If you haven't done so yet, please pause the video and try to answer the question before listening on. In order to draw the free body diagram, we're going to have to identify the forces that are acting on this positive charge. Now we can see that we have an electric field that's pointing at an angle that the question says is 37 degrees with the horizontal. The phrase with the horizontal can be a bit confusing, but we can see this dotted line right here, and the question is trying to indicate that that line right there is the so-called horizontal. It's almost as if somebody is standing here and they're sort of looking out in this direction. The horizontal would just be this dotted line right here. So this charged sphere, in essence, is actually floating here, and we'll have to draw the forces in order to come up with the free body diagram. So here's the charge over here. Perhaps the most obvious force would be the gravitational force, which always pulls objects downward towards the surface. So we could label that force as the gravitational force, whose expression is mg. We also know that the charged sphere is attached to this string right here. And so the string is actually going to be pulling the charged sphere to the left. And typically we call forces that are pulling via a string tension. So we can label that force T for tension. There is a third force acting here, and it turns out to be the electric force. We have to recall the concept that when we have an electric field pointing in a particular direction, and then we place a positive charge in that electric field, that charge will experience an electric force, and that force will point in the same direction as the electric field. So the electric force in this little diagram would be pointing up and to the right in the same direction as the electric field is pointing. Now in the diagram, the electric field is also pointing up and to the right, and so we're going to have an electric force that's pointing up and to the right. We can perhaps label that Fe. And so this diagram would be the final free body diagram, and thus the correct answer to part A. Now, in order to proceed, what we have to do next is break the forces into their x and y components. We can see that the tension force is pointing exactly along the negative x direction, or the negative x-axis. And so that force actually is already broken into its x component. This force, the gravitational force, is pointing along the y-axis, and therefore it's already broken up into its y component. It's the electric force that really we have to do a little bit of work for, because we have to find both the x and the y component of the electric force. Now we have a 37-degree angle here, as noted in the introduction to the question. The x component right here is adjacent to that 37-degree angle, so we know that that's going to be the electric force times the cosine of 37 degrees. We would be using cosine because that component is adjacent to the 37-degree angle. This component, the y component, is opposite to the 37-degree angle, so we know that will be the electric force times the sine of 37 degrees. Now, in free body diagrams, once you've broken them into their x and y components, the forces that is, you can actually erase the original force. So we're going to go ahead and remove the original electric force, because all that we really need to be dealing with are the x and the y components of these forces. Now the question notes that the sphere is in static equilibrium. Whenever an object is in static equilibrium, we know that the sum of the forces in the y direction will equal 0, and also the sum of the forces in the x direction will equal 0. Let's begin with the y forces. We can go back to our free body diagram, and we can see that there are two forces acting in the y direction. We have the y component of the electric force and the gravitational force. Note that the y component of the electric force is pointing upward, so it's going to be positive, and then the gravitational force is downward, so it's going to be negative. We're going to fill those two y forces into this equation over here. We will next recall that the electric force is equal to the electric field multiplied by the charge. And so we're going to replace Fe with that expression, electric field times the charge, and then we'll fill in the rest. Now we're trying to solve for the magnitude of the electric field in part B, so we have to add mg over to the right side, and then divide both sides by q sine 37. Now we just plug in the known values. The mass was given to us in grams, so we're going to have to convert that into kilograms. So don't forget that to do that, you just multiply the 5.8 by 10 to the minus 3. That will get it from grams into kilograms. G is the standard value of 9.8, and then Q was given in microcoulombs. So to convert that into coulombs, you have to multiply by 10 to the minus 6. So we'll go ahead and plug in. And when you compute that, you should get approximately 1.4 times 10 to the power of 3, and the standard unit of electric field is newtons per coulomb. So this will be the correct answer to part B. Now, to solve part C, let's not forget that the sum of the forces in the x direction is also equal to 0. We can see that there are two forces in the x direction. We have the tension force as well as Fe cos 37. Fe cos 37 will be positive because it's pointing to the right, and tension is negative because it's pointing to the left, so we'll fill those in. We'll go ahead and add the tension over to the right-hand side. As before, we'll replace Fe with electric field times the charge. And then we'll plug in the magnitude of the electric field that we found in part B, as well as the charge. And when you crunch that down on your calculator, you should get approximately 7.5 times 10 to the minus 2 newtons for the tension in the string. And this is the correct answer to part C. Thanks for watching. If you liked the video, please click the thumbs up icon and also subscribe so you can stay tuned for additional videos. You're welcome to send in your own question to the email address on the screen, and I'll do my best to post an answer to it on YouTube.